Hey guys, welcome to a new video. So in this video we are going to discuss educational code forces round 178 problem D array and GCD. So I hope you have already read the problem statement once. Let's understand the problem. So basically you will be given an array A of size n, suppose A1, A2, A3, A4 till AN. This array is of size n. And initially you have 0 coins. Okay, so you can either take one element and decreases it by 1, so this A4 will become A4 minus 1, or you can take one element and increase it by 1, so this A2 will become A2 plus 1. And if you decrease one element by 1, you will gain one coin, but in order to increase one element you have to pay one coin. Okay, and the constraint is unless you have at least one coin you cannot perform this increment operation. Fine, now let's see what is an ideal array. So an array will be called an ideal array if it has the following properties. Each element has to be greater than 2 for all I belongs to 0 to n minus 1 range. And second condition is if you pick any two elements from the array, they will be co-prime to each other. That means the GCD of AI and AJ, it should be 1. Okay, if any array satisfy these two conditions, then we can call it an ideal array. So let's see what is a beautiful array. So any array will be called a beautiful array if we can convert that array to an ideal array by performing these operations, increment decrement operations. So it will be called a beautiful array. So in the question we are told that we will be given an array A which is not necessarily an ideal array or a beautiful array. Okay, so you need to make some deletion operation, like you need to remove some element from this array and convert it to a beautiful array. So you are asked to calculate what is the minimum number of deletion that you can make so that the array becomes a beautiful array. So minimum deletion, count of minimum deletion that you have to find. Now let's see how we can solve this problem. Now suppose if our given array is A1, A2, A3 till AN, and the total sum is SA. SA is the sum of all the elements in this array. Now if we observe, we can see that we can convert this array to any array B, B1, B2, B3 till Bn, and its total sum is SB. We can convert this array A to array B if the following condition holds: SA should be greater than equals to SB. If this condition holds, by performing the increment decrement operation repeatedly, we can convert this array A to any array B. Okay, now tell me, do you all agree? If an array consists of distinct prime numbers, then that array is definitely an ideal array. So if this array consists all the distinct prime numbers, then this array is an ideal array. Why so? Because we know that prime numbers are co-prime to each other, right? Okay, now let's see if we can convert any ideal array of size n to another ideal array that contains the first n prime numbers. Okay, So suppose if we have an ideal array, something like 14, 15 and 11, can we transform this into an ideal array that contains 2, 3 and 5? Can we do that? Let's see. So if we factorize this 14, we get 2 and 7. If we factorize this 15, we get 3 and 5. And this 11 is a prime number. Okay. So after performing decrement operation multiple times on this 14 element, we can definitely reduce it to 2, and same thing goes for 15 as well. Like we'll convert this into 2 and we'll convert this 15 into 3, and we can convert this 11 to 5. So we see that we can transform any ideal array that might contain a composite number into an ideal array that contains only prime numbers, first n prime numbers. Okay, so this is possible. Now you might ask why I am concerned about the first 10 prime numbers. So let's draw parallel with this concept. Suppose this B is first x prime numbers, p1, p2, p3 till px, this first x prime numbers. Okay, and our given array is array A, and this one has a total sum of s of p. If we take the first n prime numbers, it will have the minimum sum among all the combination of x prime numbers. This is fine, right? So this s of p will be minimum. Now A is our given array. What we can do, we can like we saw before, right? If s of A is greater than equals to s of b or s of p, whatever, then in that case this transformation is possible. So if we minimize this s of b and maximize this s of A, our chances of converting A to B will increase. So what we can do greedily, we can sort this array A into descending order, till am. We can sort this array A into descending order, and we will maintain a running sum in this array and in this array also. So whenever we see that the running sum, let's call it sum and let's call it prime sum. Whenever we see that the sum exceeds this prime sum, we can consider that index for our probable answer. Okay, like if at any index I, if it is a zero based indexing, if at any index I this sum is greater than equals to prime sum, then how many elements we need to delete? We need to delete n minus I plus 1 elements. So we will keep updating our answer variable with this thing as long as this sum variable is greater than prime sum. Okay, so this is the solution for this problem. We will maintain a prefix sum, or we can like first of all we will sort this array A in the descending order, then we will maintain a prefix sum, and at each index we will check if the sum exceeds the prime sum. Now the question is how we can generate the list of first n prime numbers. You can do that by using sieve of erythrolysis algorithm. Okay, so sieve algorithm is very fast. You can generate first how many? First 10 to the power 5 or 10 to the power 4 prime numbers. That will be enough, because in the question if you see, our constraint is n is 10 to the in the order of 10 to the power 5. Okay, So if you can generate 4 into 10 to the power 5 4 into 10 to the power 4 prime numbers, then it should be good. Now let's check the code is pretty simple. So basically what I'm doing here, first of all I'm calling this SIF function. So I'll be calling this function once for a particular test case. Okay, and I'm passing 6 into 10 to the power 6 here. So what it does basically, it generates prime number within this range. Okay, and if you see that in 6 into 10 to the power 6 range, we can have at least 10 to the power 5 prime numbers. So let me show you the SIF function. Yeah, so this is my SIF function. This is the standard SIF algorithm, and I'm marking the boolean variable is prime, and after marking is complete, I'm iterating over the array, and if our current number is a prime number, we are adding it to a array list of primes. Okay, and this list of primes is a static variable which is defined here. Then let's see the actual code. We are scanning the input, we are defining or running some variables, prime sum for list of prime numbers and sum for our given array. Then we are sorting the given array in the descending order. Okay, and we have initialized our answer variable with n-1. Why n-1? Because I think if we delete n-1 elements, we will have one element which is itself a beautiful array. Okay, then we are iterating our array from I equals to 0 to list of prime size to minimum of list of prime size and n. Then we are incrementing our current sum, prime sum and sum. If at any point of time this sum exceeds prime sum, we are considering that index as our probable answer. We are updating our answer variable, and finally this answer variable will contain the answer for the last index for which the sum is greater than prime sum, and finally we are printing the answer. So I hope you have understood the solution for this problem. Give a like and subscribe. Let's meet in the next video. Bye.